The definition of the natural log gives us some really nice derivative formulas. So if u is a differentiable function of x, we see that the derivative of the natural log of u is just 1 over u times the derivative of u with respect to x. Sometimes this is written as 1 over u times u prime. And another nice property of the natural log is that the derivative of the natural log of the absolute value of u is the same formula. The absolute value actually absorbs, and that's a really easy proof to effect. You can see that in your notes. Now, along with the natural log, you get these nice identities. And so when you're actually computing derivatives of logarithmic functions, you can use the identities, and they work out very conveniently. So for instance, for the first problem, we have the natural log of a product. So what we can do first is use the identity that says the natural log of the product is the sum of logs. So this will give us the natural log of x cubed plus 2 plus the natural log of x squared plus 3. And again, this would work with the power rule, it could work with the quotient rule. All of these nice identities for logarithms you can use. And now when you take the derivative of y, you can actually apply it to each of these terms. So the natural log of x cubed plus 2 will have this derivative. That is, we reciprocate the argument 1 over x cubed plus 2 times the derivative of the argument, like what we have here, 1 over u du dx, 3x squared. And for this particular derivative, we reciprocate the argument 1 over x squared plus 3 times the derivative of the argument 2x. And so when you just push everything together, you get 3x squared divided by x cubed plus 2 plus 2x divided by x squared plus 3. So this is really, really very simple, and you get to utilize a lot of your pre-calculus work on logarithms. Now, of course, number 2 utilizes trig and the natural log. So y is equal to the natural log of sine of 5x. And of course, we tacitly assume that this is well defined because the argument of the natural log must be positive. So in order to take the derivative, we just reciprocate the argument. We get 1 over sine 5x times the derivative of the argument, which is 5 cosine 5x using the chain rule. And then, of course, we can dress this up. We can factor the 5 to the left and get cosine 5x divided by sine 5x, and that's just the identity for cotangent of 5x. So we would get the derivative to be 5 cotangent 5x. Now the next particular example is actually something we're going to talk about towards the last week of class. That's basically the inverse hyperbolic sine function here. Now, what's given in your text is y is equal to the natural log of x plus the square root of 1 plus x squared. But by definition, that is actually the inverse hyperbolic sine. And like I say, we'll say more about that. Now, in order to effect the derivative, we reciprocate the argument. That is, we have 1 over x plus the square root of 1 plus x squared. And then we take the derivative of the argument, which we've done many times. The derivative of x is 1. And then we apply the chain rule to this term. 1/2 times 1 plus x squared to the negative 1/2 times the derivative of the inner function, which is 2x. And now we get to use our factoring techniques, which we've used so many times, it's probably starting to sound like a broken record. So what we're going to do here, we see the 2's absorb, and we're going to factor the 1 plus x squared to the negative 1/2 here. So that will leave behind a copy of 1 plus x squared to the 1/2, and then of course the x gets left behind because it's not factored. But what we see is that this term is exactly this term, and they absorb. And we're just left with 1 plus x squared to the negative 1/2, which we can write this way with the negative removed. Now, of course, every derivative formula gives you an integral formula, so we could write this in reverse as the integral of dx over the square root of 1 plus x squared is equal to the natural log of x plus the square root of 1 plus x squared plus an arbitrary constant. Now, these are Pythagorean integrals, and they're always extended, and we'll say more about this in Calculus 2 when we talk about the derivatives of the inverse trig functions. But we will have some occasion to actually extend these integrals to more useful formulas before we end the course. And we are done.